So this is the beginning of Unit 5, which deals with 2 chapters in your textbook. One chapter is on exponential functions and equations, and the other chapter is on logarithmic functions and equations. What you're looking at here are pictures of people using a slide rule. Looks like the gentleman on the right is probably a teacher or a prof, and the lady on the left looks like she's got wings on her shoulders. She's probably an Air Force employee enrolled in the Air Force. There was a time where there was an occupation called computer. She is probably a computer. And what a computer's job was to do calculations for NASA or for the Air Force or for the Canadian government statistics department or for taxes. And they're using what's called a slide rule. And a slide rule is a mechanical calculator. It's amazing. It was invented 400 years ago almost. Like, it's been around longer than we've had electricity. This one is not 400 years old. This one is probably from the 60s or 50s. And what it consists of is 2 rulers or rules with sliding ability. One slides in front of the other. And each one, you can't really see from here, but there's an enormous amount of information on there. Numbers are all over the place, and there's different scales. And you can do calculations with this. If you take the inner slide and you move it to a certain position and line up certain things, and then you take this little guy with a line on it, which is actually called a cursor. That's where we get the notation or the word cursor from, and you slide it over to a certain position. You can add or subtract or multiply or divide or take square roots or find trigonometric ratios, take cube roots, take tenth roots. It's amazing. And a lot of these slide rules had multiple features. You can do a lot of stuff by setting it up this way, or you can take this out and turn it over, and there's a second set of lines that you can use instead. And again, it's pretty amazing. If you were cool, like I was in high school, you had a little pocket slide rule. I'm just kidding. I was never cool in high school. No, I was cool, but we didn't have slide rules. By that time, we had electronic calculators. So that's why I have this on the cover of this. It works on the principle of logarithms. And when we learn about some properties of logarithms later, I'll show you how you can use a slide rule to do some simple things like multiply or divide. Okay? I never learned how to use a slide rule in my education, so that's the extent of what I know how to do with them. People could do calculations very quickly. Okay? They had to have a very strong math background. You had to understand all the properties of numbers in order for it to work. But it's a very useful tool. Nobody uses them anymore. They're kind of, relics. What are we going to be doing in this unit? We're going to be, just to boil it down to the essentials, what we're going to be doing is we're going to be looking at exponential functions and exponential equations. So a function is a graph. We're going to be looking at what exponential graphs look like and how we can apply exponential graphs, and we're going to get into that today. And then exponential equations are equations that you're trying to solve a missing value for. It's like when we learned about trigonometric functions and trigonometric equations. We are also going to be looking at graphs of logarithmic functions and solving logarithmic equations. And in between those two, we have to learn about laws of logarithms. And logarithms and exponents are intimately related. It turns out they are inverses of each other. Obviously, if we're going to be looking at graphs of exponential functions or graphs of logarithmic functions, it follows that we're going to be doing transformations of exponential and logarithmic functions as well. Okay? And then everywhere along the way, we're going to be looking at applications of both types of those things. And we're actually going to get into an application today, at least one. So this is on page 1, obviously, of your unit handout that was on your desk when you entered the room. Today we're going to be looking at graphs of very basic exponential functions and solving problems that involve exponential growth or decay. By a show of hands, how many of you had Physics 30 with me last semester? So one application of exponential growth or decay is half-life, radioactive half-life. Okay, and that, it turns out that maybe when we get to half-life problems, you're going to want to do them with the physics approach rather than the math approach. I don't know. Either approach is fine. So to begin with, we're starting off with a definition of, I should edit my notes because I'm not saying every exponential function looks like this. This is the most basic exponential function there is. Y is equal to a number raised to the x. So c is a parameter. I feel as though I shouldn't have to say this all the time, but c is not the parameter that we used in phase shifts for sine and cosine functions. It's just a different meaning. But c has certain properties, and I don't really know that we need to get into why in detail, but c must be bigger than 0. You cannot have a base of 0. Briefly, if c was equal to 0, then this function would be y equals 0 to the x, and 0 to the x is 0. This function would be y equals 0, which is not an exponential function. It's a constant polynomial function. It's a straight line that's horizontal. And I really don't want to get into this too much at all, but c can't be negative, because if the base of a power is negative, then depending on the value of the exponent, the whole power can be positive or negative, and it dances all over the place between positives and negatives in different places. So we have that restriction. And c is not allowed to be 1. And the reason c is not allowed to be 1 is if the base of this power, c to the x is a power. It has a base of c and an exponent of x. If this power has a base of 1, just like if this power has a base of 0, this function just becomes a constant polynomial function. If, on the other hand, we have a base of 1, well, 1 to the x is always going to be 1. So we also have something that's not a unique type of function. It's just a constant polynomial function. So I've chosen to indicate this by saying on a number line that c cannot be 1 or 0. So that's why we have those open dots there. But c can be any number that's positive as long as it's not 1. So it can be anything between 0 and 1, or it can be anything bigger than 1. You catch my drift there with that graphic? That graphic is very important. So examples of exponential functions would be things like y equals 1.35 to the x, y equals 2 to the x, n of x, which is a physics equation, equals 1/2 to the x. That's what we would use for half-life. So example 1 is teaching you a number of things. In general, what these y equals c to the x look like, but also the role that the base plays in the function. Okay, this is the most important part of this first example, is determining what does that base mean in terms of the graph of the function. So we want to graph a function and then give all this information. And we're going to go old school here and use a table of values. The function is 3 to the x equals y. So I want you to note that the base is 3. It's obvious. I don't know that you need to write base equals 3. It's obvious. Okay? And your textbook, by the way, we'll talk about this later. Your textbook uses, and don't get ahead of me here on this, your textbook uses, I think, C for a base, and the diploma exam and formula sheet uses B for a base. Okay. I'm going to start at the middle, and if x is 0, then 3 to the x would be 3 to the 0, which is 1. Any number to the 0 is 1, except for 0 to the 0, which is not defined. But that doesn't matter today. And I'm going to move on to 1 for x. If I put x equals 1 into this function, then I'm going to have 3 to the 1, and that's 3. And I want you to notice that 3 to the 1 is 3 times greater than 3 to the 0. And it's 3 times greater than 3 to the 0, not because 1 times 3 gives you 3, although that's true. 3 to the 1 is 3 times greater than 3 to the 0 because 3 to the 1 has an extra factor of 3 in it. 3 to the 0 has no 3's. 3 to the 1 has 1 3. In other words, 3 to the 1, just to make a note here, is equal to this, right? If I go to 3 to the 2, we shouldn't need a calculator or anything to figure out that that's 9, but the important feature is that 9 contains one more factor of 3. Because, I mean, look at the exponent. 3 to the 1 means 1 factor of 3. 3 to the 2 means 2 factors of 3. And the point I'm driving at here is every time x increases by 1, y is tripled. So the role of the base is the base is telling you what's happening to y every time x increases by 1. And we can work backwards, by the way. If that's true and we multiply by 3 each time we move to a larger value of x by 1, then if we go in the opposite direction, we would divide by 3. And this is a third. And we know that this is a third going back to, I guess, Math 10, where we learn that if we have a base raised to a negative exponent, it's equal to the reciprocal of the base raised to the positive exponent, a very important feature of exponents in this unit. All those exponent laws are going to be crucial in this unit. And that would mean this is 1/3 as great as 1/3, which would be 1/9. So when we graph this, you're going to put a point at 1. The y-intercept will be 1 because when x is 0, y is 1. And then when x is 1, y is 3. And from here on in, we shouldn't need a table of values. Y is tripled every time x goes up by 1. It starts at 1. I triple 1 to get 3. I triple 1 to get 9. I go in the opposite direction, and I divide by 3 to get 1/3. And if I were you, I would stop there. We have to sketch this graph, and if I were to put in the point 1/9, that's very close to the x-axis. So it becomes difficult to sketch. Before we sketch it, if I were to go to -3, the y-coordinate would be 1/27. And if I were to go to -4, or -12.8, or -1 million, the y-coordinate is still going to be some positive number. Really tiny. Will the y-coordinate ever reach 0? No, I keep dividing by 3, but I can't divide a non-zero number by 3 and get 0. And what that means is that we have a horizontal asymptote here. This is a different dotted line than we were drawing with trigonometric graphs. Those were guidelines. This is what we call a horizontal asymptote. Funny spelled word. I'm just running through my head here. We did talk about vertical asymptotes in this course with the tangent function. And you did talk last year with certain functions about vertical asymptotes as well, but I don't know that we've seen a horizontal asymptote in this course. We talk about them in calculus, and I never really bring it up that in calculus class that if you haven't taken 30-1 yet, that's new to you. But it's just a line that the graph is getting closer and closer to. So when we sketch this, it's going to look, and I'm going to try to do this in one fell swoop, but it may not be pretty, so I may have to erase it. I want to draw a smooth curve through those points, and it's probably going to look approximately like this. That's pretty good. I'm having a good day. I wouldn't draw that line on the left too far to the left. I would just leave it kind of where I've landed it and put an arrowhead on the end of it and call it a day. So that's what the graph looks like. What were we asked to do here? We were asked to determine the domain. Well, look at your graph or look at the equation of the function. The domain is any real number. You can take 3 and raise it to anything. You can raise it to positive numbers, negative numbers, 0. And by the way, just looking at the graph, you can see that the graph extends forever to the left and forever to the right. It gets steeper and steeper to the right, but no matter how big of an x you can imagine, 10 million, the graph will exist there. It will just be very high above the axis. So x is any real number. However, y is always going to be above 0. It'll never be 0 because of that asymptote. That asymptote is like a limit. When I say limit, don't think limit, calculus limit for you Math 31 people. It's a limit, it's a barrier to where the function can't actually reach. There is no calculus limit, because no matter how close to zero you get, you can get closer. Okay? I guess it is zero, it's approaching zero. And that's the definition of a limit. But in terms of this function, we don't want to talk about limits. Y is greater than 0. That's it. X-intercept, well, there aren't any. Y-intercept, y equals 1, or better yet, 0, 1. Where is the horizontal asymptote? The horizontal asymptote is at y equals 0. Make sure you get that straight. It's the x-axis. The equation of the x-axis is y equals 0. All right, what if we had 1/2 to the x? Well, we can start at 0. 1/2 to the 0 is 1, which brings up an interesting point. For all of these simple exponential functions, y equals c to the x, the y-intercept will always be 1. Which isn't a very useful idea in terms of applications, but we're going to have to go with it for the time being. If I were to take 1/2 raised to the 1, I get a y-coordinate here of 1/2. 1/2 raised to the 1 is 1/2. So if I were to plot that point, I come to the conclusion that when I increased x by 1, y got cut in half. And that totally makes sense. If I were to go to the 2, 1/2 to the 2, that's 1/4. The reason why this is being multiplied by a half in going from 1/2 to the 1 to 1/2 to the 2 is because we have an extra half in the power, because the exponent is 1 greater. And that would mean if we go in the other direction, you would have to be doubling, or half of 2 would give you 1, half of 4 would give you 2. And just to demonstrate this, if you were to take a look at -2 in brackets, pardon me, if you were to take a look at 1/2 in brackets raised to the -2, that's the reciprocal. Normally we would say 1/, but why don't we just flip this guy upside down and change the exponent to a positive, and you get 4. So that means this time this is doing the opposite, which is to say as we move from left to right, in the previous example, we were multiplying by a number to get a bigger result. Here we're multiplying by a number to get a smaller result. Or it's getting bigger in the opposite direction. So this is what it looks like, 4, and then the next one, I don't have it here, but we have enough room to put 8. 1/2 to the -3 is 2 to the +3, which is 8. We are still going to have an asymptote on the x-axis. We are still going to have this shape. I'm a little off kilter there in a couple of places. It's a little wobbly, but I want to say, that's okay, but I also feel as though I can do a better job. That's a little bit better. This continues in both directions. Take a minute, please, and write out the domain, the range, x-intercept, equation of the asymptote, y-intercept. Should be a piece of cake. I'll just freeze this on the right-hand screen while I write down my work. But I think filling in that information is pretty straightforward, I hope. Other than that asymptote, there's nothing really that's new here that you haven't talked about before. You're looking at the graph, you're determining domain and range and intercepts and all of that. Any questions with that example? So I'm going to ask you to flip back a page in a minute. And I'm going to be doing this a couple of times in this lesson. This is in general what y equals c to the x looks like if c is a number greater than 1. Because if the number is greater than 1, if it's 5, y gets multiplied by 5 left to right. As you go left to right, y keeps getting 5 times bigger. So it increases. And the y-intercept is 0 and 1. This is what y equals c to the x looks like if c is a number between 0 and 1. And the point I want to make when we toggle back and forth between these two is we can call this an increasing function, and we can call this a decreasing function. Are you with me? So on the previous page where we said this, and I realize now that this graphic is a little bit different than the one on the previous page, but I hope you see that the intent is the same. What we can do is we can add this information to it. We can say now that if the base is between 0 and 1, it's a decreasing function, and if the base is between 1 and infinity, in other words, it's bigger than 1, it's an increasing function. And the reason why I want you to add this to your note package is that terminology is something that we're going to see frequently. And there's other things we can say instead of increasing and decreasing. Okay, example 2. This function, you're told, this is not an exam question. It might be one piece of a 4-piece numerical response question, like what is c equal to? It's just too simple. But you're told we have an exponential function because it's of the form y equals c to the x, and specifically it's of the form y equals c to the x. What's the equation? Well, all we have to do is ask ourselves, as x goes up by 1, what is y being multiplied by? I guess another thing you could look at is, since this is, I hope you would agree, a decreasing exponential function, left to right, it's always left to right, that c must be a number between 0 and 1. And how many of you see that c is equal to a quarter? It's pretty obvious. If I were to put it into a table of values, these data points to a table of values, I go from -2 to -1, and y goes from 16 to 4. This is an increase. I don't want to use the word increase. This is going up by 1 for x, and c is always going to be what y gets multiplied by when x goes up by 1. And we multiply by a quarter, which means that the equation of this function is y equals 1/4 to the x. And we're done with that question, but I want to elevate it now to maybe an exam question. Because, so this bit of business that I'm going to talk about here is not part of the question, but it might become part of the question on an exam. This function is y equals 1/4 to the x. But 1/4 is that. 1/4 is 4 to the -1. 1/4. And you're taught, back in grade 9, maybe grade 8, I don't know, that when you have a base, I'll use b, raised to an exponent, and the whole thing is raised to an exponent, that you multiply the exponents, right? If I have x squared cubed, I get x to the 6. So this will be a big part in this unit. I can rewrite this now as y equals 4 to the -x. And I want to I'm not asking you a question here like I'm making an exam question. I'm saying I need you to give this some thought. Would everybody agree that 4 to the x would have the same shape as 4 to the negative x, but it would look like that? Well, that's a horizontal reflection of 4 to the x. And a horizontal reflection is what happens when you put a negative in front of the x. So if we look at this red graph, which is not the graph we want, this is y equals 4 to the x, which means this graph is a horizontal reflection, which is 4 to the negative x, which is 1/4 to the x. Nobody's going to do this question that way, but I'm pointing out there's a huge connection here between reflections and these increasing and decreasing functions. All right. Functions where c is greater than 1, and I know it seems like I'm going to be repeating myself here, but it's valuable repetition, I believe. Functions where y equals c to the x and c is a number bigger than 1 are increasing functions, but we use them to model exponential growth in the world. Okay? So we use this when we figure out values of money in an investment. We use this to figure out numbers of bacteria or virus in a population that's growing exponentially. We use this to figure out the value of that Mad magazine I bought in 1972 that's been increasing in value over the years. Okay? On the other hand, if c is between 0 and 1, which is a decreasing function, we call that exponential decay. And the word decay doesn't mean necessarily what you think it means, like rotting or falling apart. That's not what it means. Decay mathematically means decreasing regularly or exponentially. And examples of that would be radioactive decay, which if you took Physics 30, you have some knowledge of, and if you haven't, you have no knowledge or little knowledge of. The value of a car. You know, I'm driving a 2011 Dodge Ram. I didn't buy it new, but if I bought it new, it would have been worth something, and over time, it depreciates. The value goes down, and it goes down exponentially usually. Now, if I take care of that truck and I keep it for a long, long time, that process might reverse because it can become a collector's item. It's not going to be. It's not in the right shape. But now I want you to go back to that first page. You're going to have to flip back a couple of pages. And we know that if the base is, I wrote the word base here, by the way. I don't know if I have that in your handout, but you know, we can use any letter we want for base. It doesn't have to be C. We've already got this written down, but now you can add this. That if it's a decreasing function, we use that as a model for things that are experiencing exponential decay. And if it's an increasing function, so the base is bigger than 1, we can use that as a model for things that are growing exponentially. So please make a note. We're not too worried about your formula sheet just yet. We'll talk a little bit about it today in detail and a lot more tomorrow, but just make a note that your textbook uses a different letter for the parameter for a base of an exponential function. Formula sheet uses B. Which can be problematic because your formula sheet also uses B for a horizontal parameter in terms of stretches and reflections. All right, let's take a look at a few more examples. Example number 3, you're given a graph showing the mass of radium-225, which is a type of radioactive isotope. It's a radioactive substance, okay? over time, but I want you to note, and this is going to be really tricky until we get to tomorrow, that this time is not days, it's 15-day intervals. So every 15 days, according to this question, something is going to happen. A radioactive sample of radium has a half-life of 15 days, and those of you who have taken Physics 30 know what that means. Those of you who have not probably don't, but you need to know what it means. You're not going to be told this piece of information on an exam necessarily. You're expected to know that a half-life of 15 days means it takes 15 days for half of the substance to decay. It changes into something else, but it doesn't matter. So every 15 days, half of the atoms change. We don't need to get into the physics of it, but you just might be interested in this. It isn't that 15 days go by and then all of a sudden at that point in time, half of the atoms change. They change over time gradually. It's not dropping like steps going down to a basement. And you're given some data here. At the beginning, there's 1 gram. After one 15-day period, so this is actually 15 days, there's half a gram, etc. What is the initial mass of radium-225? Well, initial means T equals 0. So we go over to T equals 0, and that's right here. We can see it's 1 gram, which is the y-intercept of 1. Obviously, exponential decay works whether you start with 1 gram or 1,000,000 grams. The y-intercept of c to the x is always 1. So if it's 1,000,000 grams, we have to change that equation, and we will get to that in a bit. What value does the mass approach as time passes? It approaches 0 grams. Because this is an exponential function of the form y equals c to the x, there's a horizontal asymptote there. Okay, I'm going to talk about math right now. I'm a math teacher. This graph will never reach the x-axis. Now I'm going to talk as a physics teacher. The graph will reach the x-axis because sooner or later you'll have 1 atom left or 1 nucleus left, and it will decay. We don't need to split the difference there. It doesn't matter. Okay. What are the domain and range? Well, what's the domain? It's an exponential function, but it's not any real number. Its t is greater than or equal to 0 because you can't have a negative time. And again, I know that you Physics 30 people understand sooner or later it's going to stop because that last nucleus will finally give out and decay. But this is a math class. So mathematically that graph goes on forever. What will the range be? Well, the mass is going to be between 0 and 1. The largest mass this sample ever has is 1 gram, and then it drops, and the lowest it can reach without actually reaching it is 0. So it's important that you notice I didn't put an equals to on this inequality, right? Write the exponential decay model that relates the mass. Well, this is a function of the form y equals c to the x. All you need to do is look at that information and figure out what c is. What is happening to the mass every time x goes up by one 15-day interval? Well, it's being divided by 2. There's nothing wrong with putting 0.5 here. You could put a half if you like, but it doesn't matter. Notice that the mass is being cut in half every 15-day period, not every day. If we had time in days, we would have to have a totally different equation. Estimate how many days it would take for the radium to decay to 1/30th of its original mass. Well, 1/30th of the original mass is 1/30th of a gram. 1/30th of a gram is, that's one. I got to kind of, it's half, which is maybe a quarter, 1/30th, 15. It's somewhere around here. I don't know. Maybe a little higher. Does that look like 1/15th of the total distance going up? I could even make it bigger. It doesn't matter. But this is 1/30th of a gram. And what we are interested in is that time. So how do we do that? Well, I don't think we should be reading this. Do you agree, looking at this, it looks to be more than 3? It's definitely more than 3. I don't know. I don't think it's going to be 4. We could take our calculator. What's 1 divided by 30? 0.03 repeating. Okay, so we could do a little kind of trial and error here. If I take that 0.125, which is the mass at 3 days, and I divide it by 2, I will find the mass at 4 days. And divide it by and divide it by 2, I will find the mass at 4 days. Has it reached 0.03 repeating yet? No. So it's actually more than 4 days, which tells me I probably didn't draw this very accurately. But that's okay, because we're not going to solve it by looking at the graph on paper. We're going to solve it by looking at the graph on our calculator. We're going to take 1/30th equals 0.5 to the x and solve it on our graph, because you don't know how to solve this algebraically yet. To solve it algebraically, you would need to know about logarithms, and we don't know anything about logarithms yet. So I'm simply going to go y1 equals y2 what do we get here? 1 divided by 30 and 0.5 raised to the x. I'm going to set up my window settings manually to kind of mimic what we're looking at in our example. I'm going to go from 0 to 6. We've kind of established that it's going to be around 4. So 0 to 6 I think is fair. And for y, we'll go 0 to 1. We don't even need to go all the way up to 1, because we just want to see the part of the graph that's going to reach 1/30th. But I want to do that so that I can show you that what we're looking at matches what we're talking about. So what I am interested in here is this point of intersection of this curve and this horizontal line. I don't know that I've ever mentioned this to you, but as long as the point of intersection is visible on your screen, as long as you have only 2 functions, and as long as it is only one point of intersection, you don't need to do any scrolling. Just go enter, 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 and it can find it. 4.9. 4.907. So t, x, whatever you want to call it, I guess I'm going to stick with x because I had x up here in my equation. I've got t on the graph, it doesn't matter, is 4.907. 4.907 what?
15-day intervals.
15-day intervals. So to find out how many days, we're going to have to multiply that number by 15. So the actual time in days is going to be 73.6 days. Of course, you could solve this whole question without even thinking about the 15-day intervals by building a physics 30 equation. All right. We have one more thing that we need to discuss and then one more set of examples. So, everything we've talked about so far has been dealing with exponential functions where the y-intercept is 1. But very often in these applications, x is a time. And if you think about a y-intercept, I'll even jump to this. If you think about a y-intercept for a graph where you have time on the horizontal axis, then that y-intercept, by definition, is the initial amount of whatever is changing. If this number here, if this y-intercept is 1,000, then that means whatever this is, maybe it's mice, that at the beginning there are 1,000 mice. If this number is 1,200, and the thing that is changing is dollars, then that means when t is 0, I have $1,200. So 1,200 is the initial amount. But that's no good for everything we've learned so far because the y-intercept for everything we've learned so far is 1. So how do we handle that? Well, this base exponential function of y equals c to the x, first of all, becomes y equals c to the t. We don't use x on the formula sheet. Okay, we use t, because most of the time it's t. But most of the time, the quantity that's changing does not have an initial value of 1. It has some other value. So what do? We take this, and this point would be at 1. 1,200 is a bit of an exaggeration, but let's say that this is actually up at 14. What can we do to this graph so that it will still be asymptotic and it will still be growing at the rate it's growing at, but it will pass through that other point? You multiply the function by 14. You stretch it vertically by 14. By the way, the reason why we don't want to shift this up 14 is because then the asymptote goes with it. So the bottom line here is we introduce a parameter a, and this now is the following function. So we can use this to solve problems. Y equals a times c to the t, which is not on your formula sheet. It's there, but there's other stuff added to it that I don't want to get into, is what we're going to be using for the last example. So that makes this y-intercept now a, not 1. You can even see mathematically if you put 0 in for t here, you're going to get a. Okay. Please follow along up here. Please don't get too far ahead of me, because there are subtleties. I see that some of you are doing the example now, but there are subtleties involved that you're not going to get just doing it on your own. So in this formula, y is the quantity that's growing or shrinking. T is the time. It's the number of applications of C. If C is 4, then it's 4 15-day periods, or it's 4 doublings, or it's 4 compound interests. And A is the initial amount. So here's the final example. C obviously is the, remember I told you that C is the what you multiply y by regularly? I call it the factor of change. In our first example, C was 3. The factor of change was 3. It was tripling regularly. So we have 2 towns. Allentown, whose population is currently 75,000 people, but it's decreasing at 5% per annum. Annum means year. Population of Brementown is currently 10,000, but they are increasing at a rate of 9% per annum. So I don't know what's going on in Allentown, whether it's a zombie apocalypse or a bad economy or whatever. People are leaving, okay? And I don't know what's going on in Brementown. Business is booming. Real estate is cheap. They have free festivals for the children every Saturday. People are moving there. In order for us to build an equation for each of these, which is what we're asked to do, we're going to use this general function. And t is going to be the number of years, because every year we know what happens. So for Allentown, the population of Allentown will be the initial population of, what do we got, 75K, times the base raised to the t. So my question is, I would like everybody to figure out what the factor of change is for Allentown. What is the population being multiplied by regularly? And now I have a second question. I'm going to give you time to think about that, but how many of you know immediately what that number is? Very few. This is something, when I teach Math 20, we talk about in geometric patterns, and I really try to stress it. Let's try something together. Can you please take 75,000. You're not going to do this every time. It's too much work. And I want you to find 5% of 75,000 and then take it away from 75,000 to find the population that you have. How is my math? Is that right? Okay. I want you now to find out, and I won't be able to do this, and we're going to get a part of a person, but that's okay. I want you to find out what 5% of that is and take it away from that. .05 times 71,250. Yeah, we're getting half of a person. Let's not worry about it. We're talking math right now. And I'm going to take 71,250 and subtract that. 67687. 0.5. Now, the base is the number that you multiply by regularly. How can we figure out what you multiply 75,000 by to get 71,250? Well, we can take 71,250 and divide by 75,000. Right? 75,000 multiplied by that base has to give us 71,250. So we can divide both sides by 75,000. And we could do that for the next step as well. I want you to do that. I want you to take 71,250 and divide by 75K, and then try taking 687.5 divided by 71,250. Riley, is this matching what you suspected? It's 0.95, isn't it? Why should this, we can fill this in now, why should this be 0.95? Can anybody explain why that should be 0.95? Because you would have to be able to explain this on an exam or an assignment. Patrick.
Because it's decreasing by 5%.
Right. It's decreasing by 5%. 100% is 1 in decimal form. Or think of it this way. If we have 100% and you lose 5%, what percent are you left with? 95%. But 95% is 0.95. So does anybody want to take a stab? Brementown, The initial population is 10K. Does anybody want to take a stab at what the base of that exponential function is going to be?
1.09?
1.09, because it's growing by 9%. So if you take 100%, what you start off with, and you add 9% to that, you get 109%, but in decimal form it's 1.09. And you have to be able to explain this on a written response question. So we're done. That's it. For A. B. How many complete years of change will it take for Brementown to finally surpass Allentown? And there's a misconception here. I don't know. I hope none of you think this, but I'm talking about how many complete years will it take Brementown not to reach a population of 75,000, but to reach the population that Allentown will have at that point in time. So if you were to look at this graphically, Brementown starts lower, doesn't it? And goes up. Allentown starts higher and goes down. We'll talk more about this in the coming days, but I hope you understand that since Brementown is growing at 9% and Allentown is decreasing at 5%, this is an important idea, that the severity of Allentown's curve is less than the severity of Brementown's curve. Let that sink in. Because 5% change, I know it's 5% loss, so it's going down, the red graph is going down. 5% is less than 9%. So what you want to do is find this intersection point. We're going to do it graphically, because if you tried to solve this equation, everybody, well, you can't, because you need to know how logarithms operate, and that's not possible. So we're going to do the y1, y2 thing. And then I will show you another thing that we could do instead. So I have 75,000 multiplied by 0.95 raised to the x. I don't need brackets around that base. I would never need brackets around the base. I might need brackets around an exponent if it's more than x. Oh boy, I hope this is obvious. This on the left-hand side does not mean 75,000 times 0.95 and then raise it to the x, right? Exponents come first. My y2 is 10,000 times 1.09 raised to the x. I'm going to set up my window settings by making sure that my y goes up to at least 75,000. I want to see that 75,000 at the peak at the beginning for Allentown. I don't know what I should go up to for x. So I suppose what I could do is go x equals 6. Let's just do x equals 6. Okay? And the scale here, I don't want to have a scale of 1. I'm going to go a scale of 10,000. But that doesn't really matter. So when I graph this, there's Allentown. People are leaving Allentown. Here comes Brementown. People are arriving in Brementown. Maybe some of the same people that left Allentown. And I can see here that 6 years is not enough. By the way, I could go to my table and start scoping it out there. In fact, I could answer the question by going to my table, and I'll show you that in a second. But I'm going to say, let's go up to 25. I really don't know the answer to the question, but exponential curves are hard to judge. 25 should do the trick, I would think. I'm guessing that if you have a fancier calculator than mine, it's graphing quicker. Oh, we got it. Intersect $14.65. The answer is going to be 15 years. because it says how many complete years. So after 14 years, it hasn't happened yet. We have to wait until 15 years in total. The answer is 15 years. By the way, we could go to our table, start at 0 and go up by 1 automatically, because we're looking for a whole number, right? Or a natural number. And then just start scrolling. Looking at the populations, Allentown is in this first column, Brementown's in the second. At this point in time, at 11 years, Allentown still has more people. Brementown is still catching up. So we can keep doing this. Well, 14, it's close, but by the time you hit year 15, it's happened. So 15 complete years of Allentown losing people and Brementown gaining people does the trick. If it said to the nearest tenth, which it might say on an exam, then you would do it on the graph and you would round that number we got to the nearest tenth. Any questions with the final example? All right. So tomorrow what we're going to do is fix that problem that we had with the radioactive decay where we had to have X or T as the number of 15-day intervals. We're going to say, what can we do if X is the number of days? And that will be different. All right, so page 342, you have a variety of questions that you can work on for practice. Fairly basic stuff. It all centers around y equals c to the x and y equals a times c to the x.